Now I would like to introduce our next speaker, Marta Hasny. She's a second-year PhD student at Helmholtz Munich's Institute of Machine Learning for Biomedical Imaging, supervised by Julia Schnabel. Her research advances multi-modal learning, focusing on integrating vision and tabular data to enhance cardiovascular disease understanding. Welcome.
Okay, so thank you for the very nice introduction, and hello everyone. Today in my talk, I would like to talk to you about my recent work on robust Vision-Tabular Learning with missing values. So nowadays in medical imaging, we are lucky to be able to work with large population studies such as UK Biobank, and we would really like to use this large data to actually pre-train models that we can use in the clinics. However, it doesn't come without some challenges, because in the biobanks, we also have a lot of very rich tabular data that provides complementary information to just the images. And for this reason, we would also want to use that for the pre-training. However, what happens in the clinics is that they simply don't have time to collect such extensive tabular data, and so that creates this disparity and also uncertainty of what tabular attributes will we actually be able to use at inference. So from this, two main research areas came out. The first one is where the methods try to use both the tabular data and images at pre-training and do some sort of knowledge transfer, so that you can transfer some information from the tabular data into your imaging encoder and then do inference using only images. Then the second area would be using also Vision-Tabular pre-training, but also for Vision-Tabular inference. But in this case, you also need to adapt to the missingness and uncertainty of tabular data availability, which is not really the case in the first method, because you simply use images. But from this, what we have realized is that there is no connection between these methods. So pretty much you either have to only use images at inference, or you are kind of forced to have both images and tabular data. But there is no unified model that would allow you to do both and also do it with some nice performance. So we also look into some limitations of the prior Vision-Tabular works, and what we found is that actually when the tabular data is highly incomplete compared to your pre-training set, the performance actually falls below just image-only baseline, which is obviously not something that you would want, because if you use more data than you would assume, the performance should be better than if you simply use images. And furthermore, we also realized that as you use more tabular attributes, it also doesn't mean that there is a performance monotonicity of more attributes equaling better performance, which is also an assumption that you would have, because if you use more attributes, you would also want to achieve better performance. But most likely, because some of the attributes actually introduce noise, they make the predictions harder for the model rather than easier. And so this is what we try to address in our method called RoVTL for Robust Vision-Tabular Learning. So our method is based on two main steps. We first do contrastive pre-training to pre-train our encoders, and then we actually use them for the downstream task tuning. And what differs us from prior works is that we actually address tabular data missingness at both pre-training and fine-tuning. So what happens at pre-training is that we use this augmentation that we called missingness simulation, which pretty much means that we just simulate missingness, so we drop some attributes, and then we use that for the contrastive pre-training, which allows our encoders to become robust to missing values and learn meaningful representations even when some attributes are missing. Then we use the tabular missingness again at downstream task tuning, but here we complement it with a tabular ranking loss that we call TabMoFe, which I will discuss more in detail soon. We also use a gated cross-attention module for the multi-modal fusion, where the gate allows to suppress those noisy information and allow better performance monotonicity. So now looking at our tabular ranking loss that we call Tabular More versus fewer. So here we once again operate on this assumption that adding more tabular attributes should not have a negative impact on the performance because we have more information. But as I mentioned, that's not always happening, most likely due to the noise that comes from some attributes. So we need to teach the model to actually suppress those noisy information. And so what we did here is that we sample two sets of our table, and those sets, one of them is larger, T plus, and then another one that is smaller, T minus. And the smaller subset is a subset of the larger one. And what we do here is that when the loss of the subset with more data, which should have better performance, is higher than that of the one with less data, which should have worse performance, then we have this additional loss that puts more focus on the subset with more attributes. And so what we try to do here is try to suppress the noisy information. And then we combine this loss with an actual multimodal loss. And then, once again, the TabMoFe loss is only activated when the monotonicity constraint is not fulfilled. So now, looking into some results, we evaluated the performance on different tabular data missingness scenarios. And as you can see, our method, which is shown in purple, is always outperforming the other ones. And what is also important is that our method never fails below the image-only baseline, which is something that you would want in a multimodal method. Furthermore, we also looked into how this missingness augmentation at pretraining actually affects the performance. And so what we found is that our missingness augmentation compared to the corruption-based methods that were used in prior works, and what we mean by corruption-based is that they would take the actual table and they would switch some of the values with other values that appear in that column. So essentially what happens is that you try to align the image with information that is no longer factual because you switch the values in some of the attributes. And so for this reason, we think that's why sometimes the corruption-based approaches actually fail below the no augmentation approach. While if we do our missingness, we always give the model truthful information. However, it's partial to encourage robustness to missingness. Then we also checked the effect of our tabular ranking loss, and what we found is that it actually has a lot of effect on the performance of the gate. So pretty much with the TabMoFe loss, we actually see that the outputs of the gate depend on whether you input some important attributes or attributes that are not so important. However, if we don't use the loss, the gate actually seems to mostly focus just on the number of the attributes that you input into the model, but not so much on their importance. And then lastly, we also try to see, because one of the reasons for this method would be that you can have these encoders pre-trained on UK Biobank with a lot of attributes and then be able to apply it in the clinics where you don't have as many. So to kind of simulate that, we use this other cardiac data set called MMMs, which only has 16 tabular attributes compared to the 129 that we use for the pre-training. And what is nice is that we don't only outperform the prior methods, but we also found there is quite significant performance improvement when we have our pre-trained encoders compared to if we apply just the downstream task tuning without the pre-training. So that shows that we can actually transfer some information from those large data sets into the settings where tabular data is rather constrained. So thank you for listening to my talk, and if you are more interested in it, you can check the code on GitHub and the paper. Thank you.
Thank you so much for the very nice presentation. Do we have questions from the audience? Oh, there is one back here.
Thanks a lot for a really exciting presentation. I have a question regarding this gate and possible interpretability application. So you're saying that it's useful when there's noise. Did you check if it really detects like noisy features? Maybe you could even engineer them and put them as input?
Yeah, I mean, so, the slides are no. Yeah, but so pretty much like where we try to look if it suppresses those noisy informations is when we looked at the outputs. So we check the actual importance of the features for the model, and then we kind of assume the ones that are the least important are probably also the noise that have more noise, and this is why the gate is kind of suppressing them. But yeah, that would also be a good idea to try to really look into which ones of them are actually the ones that typically lead to the degradation in the performance.
Okay, and if I'm allowed, I would like to ask one. Okay, so it's a basic question regarding kind of usability and generalizability, because you're mentioning these tabular data, and like 128 features or 16 features, are these features actually fixed? So they have names, and you're assuming they will be always the same ones? How does it really transfer across different cohorts, different institutions?
Yes, so from the pre-training to the downstream task tuning, we can switch the features. So there is no like fixed constraint that comes from the tabular encoder. You can switch them. But yeah, which is also what we did in the MMM's data set. So a lot of the prior works, you wouldn't be really able to apply it on that data set because the tabular encoder had those like preset features. But with the tabular encoder that we use, we were able to do that. But then if you do the downstream tuning, you will kind of have to stay to the subset that you selected. So I don't think it would be that easy to then add more or, I mean, you can have less because then they are just missing, but adding more would be a bit more problematic.
I see. Thanks a lot.
Okay. Are there any further questions? Maybe I could also ask something along the same lines of usability. I was wondering if you train a model now on a really rich tabular data set, how much missingness still then works for the model? Say if I train it on like super rich biobank data and then I'm in the hospital and I only have like 2 tabular variables, would this still work, or did you evaluate how much can be missing?
Yeah, so I mean, we went down to the 16 attributes that we have like on the other data set, but then in the plots where we kind of look at different amounts of them, then we pretty much went to no attributes at all. So yeah, you can kind of, the idea is that you can apply it to any number of attributes in the end.
Okay. Fantastic. Okay, great. Well, if there's no further questions, thank you again for the presentation.